Good morning, everybody. I'm going to talk about structural fixings, a building's weakest link. And in fact, it's really good to be back here after 3 years. I actually put this together ready for 2020, and then a little bug came along and that put an end to that. So I have been able to update it a little bit. As you can see, it's part 1 of 2, because structural fixings is an enormous subject. I could write an encyclopedia about them. In fact, if you look at the catalogues, you would end up with an encyclopedia. So I'm not going to look in terms of particular manufacturers, but as I know most of you are surveyors, I'm going to give you some pointers to what to look for, because a building will only fail at its weakest link. So if we can watch the weakest links, then we can actually do our clients a better service. So we're going to start. So this is 2 parts. Today is part 1, and next time you see me will be part 2. So today I'm going to be talking about starting with the basics. Now when I talk about structural fixings, you probably think of raw bolts and all these lovely sophisticated things. This is a structural fixing. It might look like a piece of bent wood. In fact, it's oak. But it's very much used, and it's still used today. So I'm going to talk about corrosion of metal fixings, because most of the fixings we use are made of some form of metal, and how that is affected by the electrochemical series and the electropotential differences. If you understand this, you will understand a lot more about fixings and why things corrode and why things fail. And we're going to look today at wood screws, coach screws, and finish off with bolts. Part 2 next time, I will carry on just as a little taster. I'm looking at long bolts and through ties. These are the ones that go right through a building from one side to the other. Structural timber connectors, which we use a lot of. Hot form rivets, mechanical fastenings, chemical resin fixings, cementitious fixings, cast-in fixings, ones which are very often abused. You will see contractors, designers specifying cast-in fixings, and the contractor comes along, we're not going to use those, we'll use drilled ones afterwards. Do you remember the Boston Tunnel? The roof panels collapsed because they changed the fixings when they shouldn't have done. So cast-in fixings are very useful and very important, and they work very well. And next time we will finish with cladding fixings. So a word about standards. Now there are lots of standards for fixings depending on what they are. So I certainly am not going to go through those because that would take forever. But be aware that for every fixing, apart from the wooden one, there is a standard. And they change over time. We make technological progress. So whereas before we used to have iron nails, then we had steel nails, and now we've got stainless steel nails. So the standards change over time. Some of the ancient fixings that you'll see in the presentation have no standards because they were built before the standards existed. And then there's a question of standardized threads. If you know about the threads, and Mr. Whitworth, who designed the Whitworth thread, then you would know when they were made individually by blacksmiths. So one nut will only fit one bolt, it won't fit the next bolt. So Whitworth did us a great service by standardizing the threads. And there are also standards for nails and screws. Most of them are British standards, but there are also ISO standards as well. There's a particularly interesting ISO standard, which is for fixings that go into cracks, would you believe? And there are some fixings that you can actually use in a crack. I haven't done it myself. I think it's a bit risky, but there is a standard for it, and it's an ISO standard. So let's start at the beginning. My favourite, the wooden peg. These have been around since long before we had metal. And this one I got as a sample. You'll find them in historic buildings because we had them before we had metal. But you will also find them in new buildings. and you'll find them in a lot of new buildings. Garages, Grand Designs type houses. There was one on Grand Designs built up in Scotland, which is timbers, large timbers, all joined together with wooden pegs. And green oak structures. Most of the new ones that are built these days are all green oak structures. And here is one, this is a very ancient one, to make my point about buildings which are historic. Very nice one. There's lots of brickwork in it, but it's only just filling the holes because it's basically a timber frame building. And you see, if you look at it closely, you can see the little pegs here and a nice bit of infill there where something has shrunk. And the timber's decaying a bit. There are cracks in it, but it's still there. It's still doing its job, and it will probably do it for another 100 years. And the structural fixings are all just wooden pegs. This is a new one. This was only built a few years ago by someone who had lots of money and decided to have a green oak wooden pegged garage. So it's rather nice. Very not unusual by any means, but you can see from the joints here, you've got a lovely lap joint here and the pegs and the braces just to hold it all together. So although it looks like a bit of wood, they are structural fixings, and they're in big buildings as well. This one I saw, this is a much bigger building, but again, all built with wooden pegs and timbers. If you want to go out for lunch, then I would recommend this place. Again, this is all timber framed, and it's all done with pegs. Can't see them there with the light. See them better in that one. And these are really important timber pegs because they're right next to the bar. Yes. So even in a big commercial premises like this, of course, with these large timbers, you will get shrinkage because when your green oak dries out, it shrinks. And here you can see some of the cracks which are appearing in the timbers. Very rarely a problem, but you can see in this one quite substantial cracks, but the pegs are still holding firm. Right, enough of timber, let's go on to metal. So we'll talk about corrosion of fixings. Wherever you have a metal, there is a potential for corrosion. And corrosion's not very good. You can actually get timber decay of the pegs. Very unusual. I have never ever seen a case of timber decay in the pegs. Non-durable materials is a problem. Contact with other materials is a problem, and I'm going to talk in a bit more detail about that because it's something you will find. Bimetallic corrosion. Who's heard of bimetallic corrosion? Yes, sir. Jolly good. Timber decay, rot. Very rare. Wood-boring insects. They don't like oak. And as you know, when you put green oak in, you've got a high moisture content. That moisture content reduces through the life of the building. The oak goes harder. And as it goes harder, it goes really hard. I had a project. This was a very old house. And from the front to the back of the house was a timber beam that went through like that. The joists went across, and it was just supported on the front and the back walls. And the owner wanted to build an extension, so we had to put a steel beam through here to make him a nice big kitchen. To do that, and to get headroom, because the headroom in these old houses is quite low, we actually had to cut a notch about that big, that wide, that deep, out of the end of the timber beam. It took 2 workmen all day long and 2 saws to do it, because that oak beam was about 200 years old, and it was just like sawing iron. And I can see you know exactly what I'm talking about. That's why the wood-boring insects don't get in it. But as I said, it's unusual in practice. Very often it might be a sole plate or the foot of a column, or you might find the ends of rafters and ties at ease level. That very often happens with gutters. If you've got a valley gutter, something like that, people don't inspect them, they don't look at them, they get full of weeds and that, or birds' nests, and then the water gets in and it rots the ends. but it happens, but not too often. And there are non-durable materials. Now the first one we use, which we use every day, of course, is steel. And iron and steel rust quite happily, as you will see. And on this one, this is a fixing through here into a stone column. You can see here where the stone has been blown off by this patch of rust a long, long time ago, because it's now been colonised. Down the bottom here, where it's nice and white, the rust is much newer. So it is still deteriorating, and we have evidence of that over a long period of time. And unless something is done, it will continue to deteriorate as the rust expands and blows the stone apart. This is another one, the same problem. This is a handrail, but don't rely on it. If you're there, don't use the handrail, because this fixing here, this has gone a long time ago, this side has gone fairly recently. So that is now unstable and potentially unsafe. In contact with other materials, now this is a particular problem. Some of the materials we use, and the metals we use, react with other metals and other things, particularly zinc and cementitious materials. Now cement is highly alkaline, and in the presence of water it reacts with the zinc and it loses the protection that we actually wanted for it. It happens also with aluminium. Aluminium and other metals. Mixing metals is not a good idea. And it happens with salt and other chemicals. You've probably all seen the corrosion that we get from salt water, either at the seaside or what we used to get in our motor cars before they built them a bit better. And when you get these different materials, you get different rates of corrosion. So here is an example. Now, the middle bit is a bolt. And on my table here, I've got some different fixings. Please come and have a look at them when I'm finished, because you'll be able to see the different finishes, and that will help you identify a fixing when you actually go and do an inspection. But here we have a situation where the bolt here, this is hot dip spun galvanized. The washer, this one, bright zinc plated. Now they are both protected with zinc, but there is a vast difference. This one, outside, 2 years life before you get down to the base steel. In a marine environment, probably 12 months life. This one, 30 years plus in an outside environment. And there's a vast difference. And the reason is that this is hot dip spun galvanized. So it actually goes, the metal, the base metal, the steel, goes into a bath of molten zinc. The zinc forms an alloy layer with the steel, and as you take it out of the bath, then there's a layer of pure zinc on it. And they are very good. Of course, putting zinc on it actually makes the threads bigger. So you will find that the nuts you use for this are tapped oversize, especially to do that. The tapping obviously takes off the zinc on the inside of the nut, but that is well protected by the zinc on the thread, and it works very well. Certainly in an outside environment like we are here, you are looking well over 30 years or more before you are ever going to find any corrosion of that, unless something weird has happened. So look at these, and you can see on this one, you can see the pitting on it. So not only have we lost the bright zinc plating, but we've actually now started to eat into the metal itself, because steel is not completely homogeneous. There are various little cells in it, different chemicals, and these corrode at different rates and give you this pitting here. So beware of that. One of the other things which is very strange is longitudinal cracking. Now I've seen quite a few examples of this, This one here is actually a ring used for tying up ships at the quayside. But you'll notice that the steel has got all these longitudinal cracks in it. I have spent an awful lot of time trying to find out why. Because like the previous photograph, it should corrode from the outside in, albeit with some pitting. This is completely different. And even my metallurgical experts cannot explain to me why that happens. But it not only happens in fixings, it happens in reinforcement in concrete as well. And it is very, very strange. But if you see these cracks, they've got a really serious problem. So we're going to have a look at bimetallic corrosion, because where you get two different metals in contact with each other with an electrolyte, you will find a problem. And in this particular table, you look at the most reactive metals that we commonly use. There are some more reactive metals like magnesium, but we don't use them in building. The most common one we use is aluminium and zinc. You go down chromium, iron and steel. Anything above there will corrode in preference to the iron or steel. Anything below there, the iron or steel will corrode in preference to this material. But it's not quite as simple as that. You do get things like these washers here, and people will sell them as, oh yeah, that's a galvanized washer. No, it's not. If you press them on it, they will say, oh yes it is, it's electrode galvanized. What a load of nonsense. It's actually bright zinc plated. It's a plating process, and the zinc is very thin and sits on the surface of the steel. So we look at the electrode potential differences then between the different materials. If you've got two different materials in contact, you need an electrolyte, usually water. If it's salt water, even better. That works even better. You get a corrosion cell formed, and depending on the potential difference between the two metals, depends on what you need to do. So if the potential difference is less than 100 millivolts, you don't really need to do anything special to protect it from corrosion. Between 100 and 500 millivolts, you don't really need to do anything if it's normally dry. So if it's a fixing in the wall here, yeah, that's fine, no problem. If it's outside, then you really need to think again. If it's more than 500 millivolts, then you need some serious thought as to what you're going to do by way of a fixing. And it's very easy. They make life easy for us because there is this lovely little chart. I don't know if you can see that at the back. Can you read that through there? No. But this little chart is incredibly useful. And it actually lists across the top all the common metals and the same down the side. And the top one here is stainless steel. And you know from my previous one that that's right down the bottom of the series. And if you look across the top here, the little arrows show which one will corrode. So if stainless is in contact with lead, then the potential difference is 390, but the lead will tend to corrode. It's not too much of a problem because it's less than 500 millivolts. But if you actually go the other way, stainless steel across here to galvanized iron, which has the zinc on it, the potential difference is 1010. This is going to corrode very quickly, and it will be the zinc that starts disappearing. And that is a particular problem, which is why you should never mix stainless and galvanized. People do. And I will give you a good example. There was a large warehouse type building. You've all seen them, the B&Q type buildings. They have metal cladding on the outside, which is fixed to an iron steel sheeting rail fixed to the columns. The cladding, they thought, oh, this is really good. We can use coated aluminium cladding because that will last a long time, which in one sense is true. But they then fixed it with a little self-tapping, self-drilling, self-tapping screw made of stainless steel. Now, with aluminium and stainless steel in a wet environment, when it rains, there is going to be a problem, and there was. And some years after this building was finished, there was a windy day, and these panels started coming off. And we're talking a piece of corrugated metal about this wide and several meters long. Fortunately, no one was injured. But the reason it came off was this bimetallic corrosion between the stainless self-tapping, self-drilling screw and the aluminium, because where they drilled through the sheeting, the aluminium and the stainless were in such close proximity that with a little bit of rainwater, off it went, and it just corroded around the head. The fixing was still there, but the sheet had come off. So if you have a chart like this, it is incredibly useful to know what material you're looking at, what material it's going to be in proximity with, whether it's going to corrode by looking at the values in here of the electropotential difference, and if it does start to corrode, which one is going to go. So you can then make some decisions. And if you are inspecting a building, look at the fixings and see what's there, see what's around them. So how does it happen? Well, this is my little diagram. So you have a surface here, let's say it's steel, and we have a drop of water. This can be a single raindrop is enough to start this process going. And what happens in that raindrop, you actually get oxygen from the air coming in and dissolving in the water. You then get this chemical reaction happening with the iron plus the hydroxyl ions and the oxygen deposited as rust. And then you get a end product here, Fe2O3.H2O, where the electrons move from one part to the other, and you'll get a corrosion pit, like I showed you in those little washers about 2 or 3 slides ago. And you only need 1 drop of water to make that happen. And because of that reaction, you get a low oxygen content in the center of this drop of water, which acts as the anode. And then the high oxygen content at the surface acts as the cathode, and that drives the different potential and enables the steel to corrode. Right, let's look at materials and finishes. Plain steel. So, cadmium plated steel. Now, if you look at these afterwards, you'll see that's just a plain steel nail, round wire nail. You do find fixings which are cadmium plated. Now, cadmium, as you know, is below steel in the series, so it protects by putting a coat over it. But it doesn't necessarily last that long. And you can actually tell a cadmium plated fixing, usually, not always, but usually by the colour. So it will usually be a gold colour, and very often when you look at that gold colour, you can see traces of other colours in it. So it's a bit like if you put a film of petrol on water, you get that rainbow colour. You can get something very similar on a cadmium plated fixing. But they are quite similar to a bright zinc plated fixing, which is like that. And some of these are bright zinc plated and then passivated. Now the passivation is to reduce the reactivity of the zinc, and it's actually done by covering the zinc with a solution, usually chromium based, and that's what they call by passivation. But that solution can change the colour of the zinc slightly. The big difference is that if you passivate that, the whole washer will be the same colour. If you chromium plate a screw, then you'll get variations in the colour because of the chromium. So, sorry, cadmium, you'll be aware of that. You can see it in the actual thing. When it's been in there a little while, it's a bit more difficult. Bright zinc plated, I've mentioned, awfully just called BZP, and electro-galvanized if they want to sell you something cheap and nasty. Sherrodized steel. Anybody know about sherrodizing? No? Right. Sheriddizing is very interesting. It was used for things like screws, nails, fixings, bolts and that. In this process, powdered zinc and the raw steel items are put into a big chamber, and they are heated and the chamber revolves, and as it does so, some of the zinc sticks to the surface of the steel. It's not the same as hot dip galvanizing, it's not as hot, and it's a different process. And what you get from it is a dull grey finish, which is different, you can see it when you get up close, to a hot dip galvanized finish, which is usually much more shiny. I think it's probably gone out of fashion, but if you're inspecting existing buildings, you may well find Sheriddized fixings in there. You might even think that they were hot dip galvanized, but they probably may not be. Right, hot dips come galvanized, as I said, like these bolts here. You put that into a bath of molten zinc and then leave it there for a little while for the alloy layer to form, and then you pull it out and it comes coated in pure zinc. Very good, very long lasting, and if you're looking at washers, these are the best ones. These are hot dip galvanized square plate washers. You use a lot of them in structural work. They're nice and thick, they don't bend like the other ones do, and very, very useful product. And stainless steel. Now you get various grades of stainless. When I started, it was 304, 316, or various other specialist ones. Now it's A2 and A4, just because they want to change the designation. But there we are. You can generally see stainless because it looks a bit different. It's a slightly greyer colour to what you would see in some of the light coloured zinc plated stuff. And the zinc plating does tend to be a different colour depending on how they did it. And there are special materials like bronze. You might find some bronze fixings around, not very many, but they do. Historic buildings sometimes have bronze fixings in them. Now, this is an example of how not to do it. We have here a handrail to the sea. You actually fall over about 5 meters to get into the water there, so it's a very much a safety related thing. When they did it, all of this is hot dip galvanized. Fine, but perhaps not quite so fine next to the sea. But the wires that go through here are stainless steel. So you've immediately got a potential difference of 1010 millivolts and nice salt water here. And you can see, if you look closely, there's a little collar around there. And what happens? Of course, you get rough weather, you get salt spray going up there, and the salt gets on, the water comes down, it goes past the collar, and this starts a corrosion cell, and you can see the corrosion now running down from each one of these. But that wasn't a very good idea anyway, because these things are clear, not clear, the white plastic, a little white plastic collar. And as you know, plastic degrades in sunlight, especially if it's not black plastic. And these corrode and they degrade, and you can see the corrosion cell formed round here and literally running all the way down. And this was obviously a stormy day. I don't know how it managed to do this, but the corrosion cell is actually going upwards. So I can only assume that that was the result of a very severe storm at the time. And if you look at these, you can see this one is broken away completely, that one's broken away, that one's broken away, this one's yet to go. But the problem was there right at the design stage, mixing stainless steel and galvanized steel together. They also had a problem with all their fixings as well. On the same site, just round the corner, also in the seawater, is this one. Now here, they've actually put in a much larger collar, and it's black, and it looks to be not plastic, it looks more like a rubbery substance rather than the plastic. And that was built at the same time as the other one I showed you, and it's not really, there's a little bit of activity there, but not too much. And that will probably last for 30 years. And even then, you can see this pitting around here. This is another type of collar, same project, different part of the site. They've got a different collar here, and that is protecting better than the white plastic one, but not as good as the black rubbery one. Right, we'll move on to nails. We all know about nails, don't we? We use them all the time in construction. Timber to timber connections, yes. Rafter to wall plate, a particularly important connection for a nail, because it prevents the foot of the rafter going out and the roof spreading and all sorts of problems. Very often driven in at an angle and splitting the rafter as well at the same time. But there we are. That's builders. We use round wire nails. Now, this one is plain steel, which we used to use. Nowadays, for half a decent job, you'd use a hot dip galvanized nail, which I said, that in the dry environment of a loft would give you an indefinite life. It would certainly exceed the design life of the house without any trouble at all. You can get some BZP ones, but I haven't seen them for a long time. But you might find them in a structure that you actually go and have a look at, and you can tell by the colour of them. Flooring to timber joists. Ah, yes. There was a case where a building had floorboards on the first floor, very common, on joists, timber joists. The joists rest on the wall, providing stability. Builder comes along and says, ah, I'm going to renovate this property, so I need to put in lots of services. So on the first floor, he took up all the floorboards. Now the floorboards were fixed with these 2-inch cut nails. You wouldn't think that's a structural fixing, but it is. These floorboards, nailed to the joists, provided horizontal girder, basically, which was providing lateral restraint to the wall. When he took all the floorboards up, guess what happened? The wall started moving outwards. So all because of the little structural fixings which he removed when he took the floorboards up. And you get bigger ones as well. This is a 4-inch cut now. You sometimes find these in the rafter to wall plate connection. Not very often, but be aware that you can, and they are inevitably plain steel. They have no corrosion protection on them at all. I've never seen one with any protection on it. So beware that tiny things, as a 50mm nail, is a structural fixing, providing stability to the building. Cut nails have a plain finish, and the nails commonly used with metal products. Now, we've all heard of joist hangers. Now, the joist hanger is made of steel and it's galvanized through a bath, but unlike the bolts, when it comes out the bath, the zinc is wiped as it comes out the bath. That means that the coating thickness is very, very much thinner. And although it's bonded to the steel, it's much more like the bright zinc plated product. It's all right for indoors and that, but not outside. Truss clips are made the same way, although you can get both in stainless steel now. And the galvanized ones fixed with 30mm square twisted galvanized nails. Very common, find them everywhere. And the truss clips the same. Of course, when you are using stainless steel joist hangers and truss clips, you need to use stainless steel nails. Do not mix the two. And the nails 30 by 3.75 square twisted, to come off the shelf all the time. We do find a problem sometimes that the builders don't fill all the holes. So if you look at a joist hanger, it's probably got 10, 15, sometimes 20 holes in it. And they put a couple of nails, one that way, and they're off. No, that doesn't actually take the load that it was designed to. Historically the nails were plain metal, but now hot dipped and stainless steel annular ring shank nails are really good, unless you want to get it out, in which case they're a pain. But don't use stainless steel with galvanised fittings or BZP fittings. Here's a good example. You can see joist hangers, and there are a few nails in there, but not very many. And that's fairly typical of work done by builders who have no outside supervision. So if you're going to inspect a building, that's a good place to look for the quality of the work, or lack of it. This is a conversion. Here we're using truss clips in the top here. And that's just another shot, but again, they are just galvanised truss clips with galvanised nails. And here's another interesting one. These clips, joist hangers, have 2 holes in there for bolts. But because that's right up against the wall, they haven't bothered to put the bolts in. So they just put in a couple of nails instead. Not a good idea. What you could actually do is use a coach screw, which I'll talk about in a minute. So we talk about wood screws. Let's have a wood screw. Here's a nice wood screw. Plain metal, slotted head, countersunk, used for years and years and years until they decided to change them to Phillips and go up market with the screws. The Phillips head, there's several variations to that, as you know, Phillips and posi drive. Bright zinc plated, yes, you'll find those. And bright zinc plated and passivated, which, as I said, can give you a different colour to the screw. They tend to be more of a goldy colour, but the same colour. And stainless steel, of course. And we come to coach screws. Now, coach screws are really useful. I've done loads of projects where you have to put one timber against another one and the timber's against the wall, so you can't get to the back of it. You may also want to join timbers. We've done plywood splicing of timbers, particularly hip rafters, where we would use a coach screw. And this is quite a big one. This is one, we actually use ones like this on a bridge to fix the deck down to the timbers. It's a timber deck down to a timber bearer. They're stainless steel because it was a bridge and it was outside. But you can get much shorter ones, anything from about 1.25 inches. 2-inch ones we use quite a lot. And then there are longer ones, there's even longer ones than this. But coach screws are a really useful product, and they are a structural fixing. So you can get plain steel ones. You'll find them in old buildings. Very rare to find them in a modern building. The ones that are sold these days are either BZP or stainless steel. Hot dip galvanised ones, I've seen them occasionally, but not very often. Stainless ones you can get quite readily. And then we move on to bolts and nuts. So we're getting more and more into the technical side of fixings. So originally, of course, they were all handmade by the local blacksmith. So the nut and the thread will only fit together. They won't fit other nuts and bolts. Plain steel, bright zinc plated, yes. That's a bright zinc plated one, nice and shiny. Very good indoors, fine. Outdoors, no. Cadmium plated, again, as I said, you look at it, it's the gold with this sort of what I call a petrol-y colour effect on it. Hot dip spun galvanised, yes, really good. They will be grey, like this one. And stainless steel, which are a bit like BZP, but they have a slightly different colour, a different grey. And in terms of grades, now this is important because when we do structures, we actually have to find the right grade of bolt to take the load that we want to. So we had grade 4.6, which was the mild steel bolts, which we've used for decades. And now we've moved over to high tensile steel, grade 8.8. If you are really in trouble, there is even a higher grade, 10.9, but I've never seen it used in structures. 8.8 is used quite a lot. And when we look at bolts, this is a nice little building, Victorian building, with a tie across and a hanger from the ridge. If you look just there, oh yeah, yes, well, you can tell it's a handmade nut, and it's obviously not actually reached the point where it was supposed to be. This one is another one, same building, but that one's actually doing its job. But the handmade nuts are usually square. They find that these hexagonal nuts didn't come in until Whitworth started with his threads. Word about coach bolts. Oh dear. Who's seen a coach bolt used in a structural application? You, sir. You, sir. Not good, is it? These things are too commonly available. They are misused by builders on an industrial scale, and they have a load of problems. First of all, they don't comply with the standard that we want to for the strength. Secondly, the head, as you can see, is quite rounded. It hasn't got the strength that you can see in a hex head bolt. There is another problem. Underneath the head is a square section. If you put a square section in a round hole, it doesn't work. The head never actually gets into contact with the washer. Now you see these in roofs. I've seen lots of them in roofs. I've seen them in all sorts of other structural applications where they should not have been used, and we've had to go in and replace them. And that is a much more difficult problem than putting the right bolt in the first place. So that is why this is written in red. They are not a structural bolt and should not be used for structural purposes. The clue is in the name, coach bolts, invented for coach work, from when we had the days of horse and carts and carriages, but greatly misused. So if you see any of those in a structural application, you need to flag it up as a big red warning. But we do also have sort of incompetence as well. This is a nice steel frame going up for a building. Look at the bolts. Now, those bolts are the wrong ones. How do we know they're the wrong ones? Because the thread coming through the nut should be 2 complete turns. This is much, much longer than it should be. Now you say, does it make any difference? It does make a difference, because it means that the person who bought those bolts didn't really care about the fact they were long, but did they care about whether they were the right grade of bolt? It flags up a question, because then they've connected the earth wire to it as well. And you really start to worry then about the quality of the rest of the work, because if he's not putting in the right bolts, did he do the rest of it correctly? Probably not. Now my next slide I will apologise for, because it's not the quality I would normally use, but it was the only one I could get. So I'm afraid it's a bit blurred. This is an enormous hall, right across from one side to the other, and the roof has got a series of curved tubular trusses. Now this is spanning something going up towards 30 metres, and it's a really big truss, as you can see from the height. So I'll pass on to the next one, which is a bit better. But these trusses weren't made in one piece because they were too large to transport. They made them in 2 pieces, and they put the join right at mid-span where the greatest stress is, which was a really clever thing to do. But in doing that, then they had to bolt it together. And the bolts they used, this, something as small as this, to hold up that truss and the roof, spanning nearly 30 metres. It would be a good idea to get the right bolts, wouldn't it? They would probably need at least high tension 8/8, possibly even a higher grade for those, because they are performing an absolutely crucial function. And if you look at the end of them, you've got a whole series of them. But if they're the wrong ones, that's not very good. The bolts are quite easy to check because on the head you will find usually the letter M for metric, and you'll usually find a grade number, 4.8, 4.6 or 8.8. So you can tell whether it's a high tensile bolt or a normal grade bolt. Not easy to get up there and look, but that is an absolutely critical fixing. If that goes, then that whole truss goes. No, don't like that. This is another one. This is a block of flats. And here you've got a steel beam coming across here, connecting to this one. All that's holding it are two little bolts. Two like that. But they're not even like that. They're only BZP bolts. They're not even galvanized. If they corrode, that beam is going to collapse. All for the sake of putting in two bolts of the right grade. That's just a close-up of it. You can see the BZP colour on it. This is a nice building. Does anyone know where this is? No? This is the brand new, highly expensive Prestige airport terminal on the island of Guernsey in the Channel Islands. They spent a fortune on this, but when you go inside and look at the staircases, because there's a staircase that goes up to the upper level, you look at the bolts and you think, that's a bit strange. If he didn't get the bolts right, what else have they not got right? Because this was done by a big contractor. And here you can see, this is another junction going up the stairwell. Again, we've got bolts that are too long, but notice that this one was put in the other way round to all of the rest. Very strange. Problems with workmanship here. Probably problems with the buyer, not actually buying the bolts of the right length. Yes. I had to walk up the staircase to get the photo, but I came down very quickly. And that's another one. It's common. All the way through, they have used the wrong bolts. This is a big portal frame. Again, difficult to get a picture of it, but spans about 20 metres, 2 columns, standard sort of big portal frame. This is the knee joint between the rafter and the column, which is in the wall here. So this is a moment connecting joint. It is a primary joint for the structure of the building. Oh, they've missed a bolt out. There's supposed to be 3 there, there's only 2. Oh dear. And someone signed off that building. This is what they should look like. I've shown you the rubbish. Let's have a look at what we should find. We should find bolts with a washer under the nut. And I'll show you another one in a minute where you need washers under the head as well. And here's the nut, and you've got 2 threads through, and absolutely spot on. Exactly what they should be there. So the people who did this were taking pride in their work. So they probably took pride in the rest of the work they did on that project as well. This is a really big, it's Clandon House near where I live, and it caught fire and all was completely gutted. And they put this huge scaffolding frame around it. But inside it looks like this. There was very little left. And there is a big steel truss across the top here with fire protection on it, which survived beautifully. But below that, there are 2 clamps like that there, which had timber columns coming up. And those clamps, you can see here, were completely unprotected. So the timber has burnt away and collapsed. These bolts here are actually clamping bolts which clamp the plates onto the side of the timber. So they don't actually go into the timber itself. But that is highly suspect, having been subjected to such high temperatures in the fire. But the small fixings are really important. This one I like, you probably see it's a railway station. In their cantilever beams, they've got bolts through here, but they've got cylindrical heads and nuts and hexagon fixing, socket fixing in the nut to actually hold it all together. So someone took a great deal of trouble to do that, and pride, and it looks lovely. You can't even see the hexagon head. So people can do things right, but they can also do things wrong. And I come to these. This, as you can see, is a garden centre. Again, a large portal frame. But that portal frame has a critical connection here, as you can see by the strengthening. And that plate has just 4 bolts here. 4 of these. And that's all that's holding up a 20-metre span. So we need the right bolts. I cannot emphasise that enough. The fixings, the structural fixing there is the building's weakest link. The portal frame steels will be fine, but the fixings fail and the whole lot goes. This is another one. This is a very light truss, but if you look in the centre here, again, you've got a connection. In this case, 4 bolts again. This is a worrying one. The reason being that the plates here don't line up. Now, steelwork is made to a very tight tolerance, normally about 2 millimetres. So something has gone wrong there. The question is, because the plates don't line up, the holes won't line up. If the holes don't line up, how have they got the bolts in? Now, they may have reamed out the holes to get an oval-shaped hole or an elongated hole. They may have just hammered them in and damaged the threads so the nuts won't actually get a full bonding. Something very, but those 4 bolts are holding up that whole frame. Yeah, I didn't stay too long there either. And this is another one, same place, but a different part of the building. And again, if you look at the connection at the top there, this one's only got 2 bolts in it. It really is important that you have the right bolts. The structural fixings are the weakest link in that structure. And I'll move on to these. Now, we've talked about steel. Most of those were hot rolled steel sections, but now you can get lightweight, pressed formed metal sections forming portal frames. And the steel is very, very thin. This is one in question, and you can see it's a very large span portal frame because it's got aircraft inside it. And you can see here that this is just a piece of thin steel sheet bent into that shape with the bolts going through. Now, I mentioned before about washers under the nuts, but where you get a very, very thin section, we really should be putting washers under the head as well to spread that load into that thin metal so it doesn't actually pull through. And you can see how thin it is. You've got 2 of these sections together, back to back, forming the portal frame. And this is the knee joint. Again, no sign of any washers underneath the heads of the bolts. The manufacturer will probably say you don't need it. But really, when the metal's, you know, only this thin, yeah, I don't believe him. That's the apex one as well. But if you come back to proper sections, the other problem is lack of geometrical fit. And here you can see a really deep section, that's about 600 mil deep, and it's a very strong structural connection, but here, the bottom flange doesn't touch the plate. Now, these connections rely on friction, and the bolt being clamped up tight provides the friction between the plates to transfer the force. So here, that's not happening. And these 12 bolts now are all acting in shear to try and transfer the force from that side to that side. Yes, not good. And how you put the bolts in is important. This is a canopy. And you note the bolt here has been put in upside down. Now, in the event that the nut comes loose for any reason, the bolt will fall out and the canopy will collapse. If you put the bolt in from the top and the nut comes off, the canopy will still stand. So it is really important when you look at structures to see whether they were paying attention or not, because if they didn't pay attention to this, they may not be paying attention to other things as well. And high strength friction grip bolts, now these are really good things. These really clamp the steel together to give you a good load path between the steel sections. I worked on a project and I actually had to go and check them, which I'll talk about in a minute. We're used with load indicating washers. This is a load indicating washer. It's a washer and it's got little bumps on it. They're now called direct tension indicators, would you believe? Why? I do not know. They've always been called load indicating washers, but there we are. They're checked with a feeler gauge, and the fixing relies on the friction between specially prepared steel surfaces. And what actually happens, these little bumps that you can see on there, and I will show you a picture of, there they are. As the bolt is compressed, and these are high tensile bolts, these little bits sticking up get squashed. And when they are squashed to a certain amount, that is the correct tension in the bolt. And we check that with a feeler gauge. And when I was doing my training, I was given a hard hat and a feeler gauge. Go and check those beams. All we had was a ladder, no harness or anything. And we used to go up the ladder and climb along the beams or walk along the beams to the next connection. Health and safety was different in those days. But the whole point of it was that with a feeler gauge, you can check how much that has been compressed and whether the bolt is either over tension or under tension. And then you have to go back and sign it off, which is a interesting exercise. But very useful, high strength friction grip bolts or direct tension indicators if you really want to be modern. And to get this lot, I have some acknowledgements. Northwood Forestry, who are a very nice company, provided me with this. Otherwise I couldn't show it to you. Magna Fasteners provided most of the other fasteners, and Andrews Fasteners make these things. Those are the people. So, the fixings are a building's weakest link. More care needs to be taken in the selection and the actual installation of the fixings. And pay particular attention to fixings when you're inspecting a building. It's unlikely that the beam will be wrong. It's possible, but unlikely. Much more likely that there's a problem with the fixings. And there we are. Do come and have a look when we finish. But any questions? No? Good.
All the defects we found, do you inform the building owners that?
Yes. Oh yeah, we have a duty of care. We all have a duty of care in our various professions. Right. Okay.